That'll do. So, hello everyone. I'm Craig. Really happy to be here. Yeah, not my laptop, so if everything breaks, it's not entirely my fault, but we'll see how we go. So, I'm from New Zealand. Sorry if you find it hard to understand me. I'll try to enunciate. I'm an Angular GDE, so I get to do this a little bit, and I'm currently a senior architect at HeroDevs, who have, HeroDevs is a company where we specialize in handling end-of-life events for open source software. So we do things like never-ending support for some old libraries like AngularJS, Vue2, Bootstrap, Drupal, a whole bunch of things. In my role, I get to work with clients all over the world, and we help plan and roll out large-scale migrations and manage the transition from old technology to new technology stacks. And at the moment, I'm actually working with the engineering team at Rust-eze. So I'm working out of the Rust-eze Lightning McQueen Training Center and Technology Hub, which is in Radiator Springs in Arizona. And we're responsible for making sure that Mr. McQueen is performing at his absolute best so he can keep up his winning form. If you want the slides, you can grab the link here so you can follow along on your own device, or they'll obviously be available after. Before we get going though, I have a little message to play from our sponsors, Rust-eze, featuring Mr. McQueen himself.
Lightning McQueen here, and I use Rusty's medicated bumper ointment, new rear end formula. Nothing sues a rusty bumper like Rusty. Wow, look at that shine. Use Rusty's, and you too can look like me. Ka-chow!
Ka-chow indeed. Lightning McQueen. He's a little bit of a legend around these parts. 7-time Pistol Cup winner, a catchphrase master, and all-around great guy. Whatever Mr. McQueen wants, Mr. McQueen gets. And what usually Mr. McQueen wants is to go faster. Lightning is a highly tuned machine. Every system is engineered for peak performance, and we're always on the hunt to fulfill his need for more speed. The chief engineer at Rust-eze, Sir Tomater, has been Lightning's best friend for as long as anyone can remember. This talk may be cursed. I'm going to not touch that. He's often the source of the best ideas and suggestions for how to make things go faster. Speak of the devil, here he comes now.
Hey there, Frank. I have an idea to help Lightning McQueen go even faster.
Oh, that's an amazing generated AI voice there, Mater. What's your idea?
I think it's time to get the aerodynamic simulation working on Lightning's heads-up display.
Wow, that is a great idea. Lightning's always wanted to be able to update his aerodynamics on the fly during a race. One little known fact about Lightning McQueen is that all of his onboard software is written using TypeScript and running on an internal browser. As part of our ongoing research and development, Lightning uses complex aerodynamic simulations to figure out the fastest shapes to be in while he's racing. These fluid dynamic simulations use what are called lattice Boltzmann methods to simulate the flow of air over the body of a car. This is an example of the kind of visualizations that the simulations produce. Lattice Boltzmann method is a two-step algorithm which models how a fluid moves through space and interacts with barriers in that space. The first step is a collision step, which models collisions between the molecules of a fluid. And the second step is a streaming step, which models the change in fluid. Come on. Fluid density. Oh, that's getting worse. Yeah. Cool, okay. So the second step is a streaming step, which models the changes in fluid density. The specific implementation details don't really matter here. It takes quite a bit of math to get it work, but at a very high level, you can think of it as a simulation across a two-dimensional grid.
You just need to figure out how to get the simulation running fast enough to be useful during a race.
Yeah, that would be great. Whenever we tried to run it in a browser in the past, it hasn't been fast enough. Crunching all those numbers takes some time. So let's investigate it a little bit. There's two main parts to our visualization, the simulation and the renderer. The simulation class is an implementation of the lattice-Boltzmann algorithm, which takes x and y dimensions for the grid, as well as some values representing the fluid velocity and the viscosity and the simulation speed. The canvas renderer is just an HTML canvas-based renderer which colors in the grid based on the fluid velocity at each point on the simulation grid. Everything executes in a loop, one step of the simulation is evaluated, and then the result is drawn to the canvas. The web-based implementation looks something like this, and you can, again, scan that QR code if you want to actually read that tiny, tiny code. See some phones up. The end result looks something like this. No, you're going to load? Come on. Beautiful. What's going on there? Okay, well, it looks like that GIF you saw before. Put it that way. Let's see how this goes. Why is it showing on this screen but not yours? So let me just do this and see if you can see it for a little bit. Okay. Don't look at my notes. See the thing all pretty and moving? Cool. That's what it's doing. Goodness. So, unfortunately, running in the browser like that, it's a little bit janky, and it doesn't quite run as fast as we might like. If we add time logging, we can see that our simulate method is taking about 32 milliseconds per frame. If we want 60 frames a second, we need to make this about twice as fast. We need to aim for 16 milliseconds per frame. But the good news is that the rendering code is pretty quick. We can see it's only taking a couple of milliseconds to run the actual render. So our rendering code is good. Canvas APIs are fast, we know that, that's true. But the simulation itself is too heavy to get it running at 60 frames a second.
I don't know if it's fast enough for me to use it in real time. I need it faster.
Those voices are the best. Yeah, it's not fast enough, we need to make it faster. You heard the boss.
You heard the boss. Gotta be faster.
Okay, so let's get into it.
You get to work on that. I need to go put on some Rusties. Ka-chow.
If there's one thing I know about Lightning McQueen, it's that he sure loves Rust-eze. Wait a minute. That's it. Rust. Mater, what if we try writing the simulation in Rust?
Woo! That's a great idea.
Thanks, I think so too.
You'll have to teach me a bit of Rust so I can help.
Of course. Let's do a quick comparison of TypeScript and Rust. So, TypeScript is a superset of JavaScript, focusing on static typing and web development. Rust is a systems programming language, emphasizing safety, performance, and concurrency. TypeScript relies on JavaScript's runtime, so it has all the wonderful garbage collection and stuff that lives in that world, whereas Rust provides memory safety without having to use a garbage collector. TypeScript natively supports asynchronous programming, that whole model from JavaScript, but lacks native parallelism, while Rust has built-in support for concurrency and parallel code. And Rust offers fine-grained control over memory and achieves high performance, whereas JavaScript and TypeScript have those same not-so-fast runtime characteristics. In terms of tooling, in TypeScript, we might use something like NVM to manage the different versions of Node that we might want to use. In Rust, the equivalent is Rust up. For TypeScript, or more generally Node, we might use npm to install some dependencies. In Rust, we'd use cargo to install crates. To compile and build our JavaScript or TypeScript code, we might use one of many tools, like TypeScript itself, Vite, Webpack, Babel. But in Rust, we're mostly going to use cargo build. To test our JavaScript code, we're going to use one of, again, many packages. We might use Jest or vtest or Cypress or Playwright, something like that. In the Rust land, we're going to use cargo test. In general, Rust has a much tighter coupling between the language and the tooling. It's a bit more of an opinionated ecosystem.
That's all pretty neat. Well, does it look like?
What does it look like? Good point, Matter. Let's look at some code. So, we're hopefully pretty familiar with what assigning variables looks like in TypeScript, where we can create variables with const and let, with somewhat confusing implications about the mutability of the values. And this is the rough equivalent in Rust. So in Rust, by default, variables are immutable, and we need to add the mut keyword to opt in to mutability. So we get this immutability by default, which is quite a nice feature. And we have to opt in if we want something to be immutable. With TypeScript, we can import code from other files using relative paths, or packages if we're importing them by a full name. And a TypeScript file is interpreted and executed line by line. But in Rust, there's not necessarily a one-to-one mapping from files to modules. We can import a full module and move specific module members into scope with the use keyword. And then we have the entry point to the program. So it's not just executed from the top down. We have a main method. And say we want to do something like instantiate thing. This is just a convention. We're just calling the new method on this object. It's not part of the language like new is in TypeScript. There's nothing, there's no reason you couldn't change that name. So TypeScript has control flow structures like if statements, while loops. And if you pass an object into a function in TypeScript, you're always passing a reference to that object. Rust syntactically has the equivalent, right? We have some, different control flow structures there as well. They look pretty similar, but there's a few different syntactic differences. So optional parenthesis, but they mostly work how you'd expect. It's a programming language. But there are a few things different, right? So if we call a function in Rust, you need to explicitly state that you're passing something by a reference. And we're going to come back and do more on this soon. So you can get a similar programming model between TypeScript and Rust, but it's just got these few differences. So functions, there's a lot of similarities between a TypeScript function and a Rust function, because again, it's a programming language. Rust uses the fn keyword, so a slightly shorter bit of syntax for declaring one. And also by convention, they use snake case for naming functions or variables. Rust allows you to mark that a parameter must be passed as a reference or must be mutable, or in this case, both. Rust also has more specific types. So in TypeScript, where we talk about just a generic number type, or a big int maybe, in this case, ydim must be an unsigned 64-bit integer. So you have to be more specific about what types of types you're passing around. One other nice thing that Rust has that we don't have in JavaScript, TypeScript land is this kind of special range syntax. So if you've ever used any Python, they kind of look a bit like list comprehensions. So defining objects in TypeScript, we can just define an object with a type or an interface. And in Rust, we have an equivalent, which is a struct. So by default, everything in Rust is private as well. So we had default immutability. We also have default private kind of visibility. If you want to make something public, you have to specify that. So you have to say that these things are public. And again, here we can see that we have these more specific number types. Going a bit deeper into these things with more objects, in TypeScript, you can define a class, which is both a type and the implementation of that type. So you can pass around the class and use it as a type, or use it as the actual class. But in Rust, our type and our implementation are kept separately. So we have the type defined as a struct, and again, here we can see that the members in this struct are going to be private by default, because we haven't used the public keyword. And then we define the implementation with the impl keyword. Like I said before, we have this convention of defining a method called new, and that's what's used for instantiating the object. And in this case, we have a new function that returns an object that matches the struct. So it's kind of like these two parts coming together with a constructor to return us this object of this type. Basically the equivalent of something like a class. One more weird thing. Rust has this special like macro syntax, which we'll see a couple times. This is one place where it's quite different from TypeScript, where it's a way to do meta programming. So if you haven't done any meta programming, it's like programming. So you can define constructs that produce more code than it might look like in the actual syntax itself.
Oh, that looks like a programming language.
Yeah, exactly. It looks like a programming language. There's nothing too scary here, especially in this case where we're just converting something that's quite mathy. It's just some if statements, some loops into some Rust. So this is the TypeScript implementation of our simulation. Here's the first chunk. You don't need to know the whole thing. It's basically moving numbers around in arrays. Nothing too fancy there. You can scan the QR code if you want to check it out. But yeah, we're talking about looping through arrays. We're talking about doing some maths, and we're talking about moving some numbers around. For this kind of thing, it's pretty translatable between a bunch of different programming languages. And to prove that, there's the Rust version. Like, they're pretty similar if you kind of look at them. And QR code should pop up if you want to have a look at compare them. So the main things that are different is like the syntax for looping is a little bit different. We use self as a keyword instead of this. You might have seen some old JavaScript code that did var self equals this. It's basically that same thing. And we have some extra precision around the different types of numbers that we're using. So it would be really easy to look at this thing and go, okay, cool, this is just another programming language. I can convert my stuff into this world. Why all the hype around Rust? Why is the thing so special? Why is it even different? And most of the magic, most of the stuff that makes Rust such a specialized language is in the realm of memory management, which is something we don't ever really think about in kind of JavaScript land. So Rust guarantees memory safety by enforcing some basic but strict rules for how you can pass data around. So there's how you borrow data and also who owns the data. So we're going to look at ownership first. These are a little bit contrived examples, but hopefully they get the point across of what's going on. Let's say we wanted to instantiate the simulation twice for some reason. Maybe there's two different situations that we want to compare and run slightly differently. If we ran cargo build, so that's the command that we'd use to build our code, over this code, we're going to get a really big, loud, scary error. And Rust compiler errors seem pretty terrifying at first, even coming from like TypeScript land, where they're kind of these massive long things. Rust uses lots of fancy language, but it's also very good at telling you what is going on. So they're very helpful if you actually read them. It often means you have to look up those scary words in the documentation, but they're pretty consistent. You start seeing the patterns in them. And what this error is trying to say is that we passed the simulation into the initialize function the first time, and when we did that, we gave up ownership. So it's like we've given something away to our friend, and now we're trying to give it away to another friend, but we can't because we don't have it anymore. So we can't give this thing away again. That's all this error is saying. And if we want to be able to give away ownership twice, we first have to make a copy of the thing that we've got. So in this case, we're going to clone our object, which creates a new instance of that object in memory. So we now have two. So we can give away the clone, and we can give the original one away. And that's one way that you could make the borrow checker happy in this world. But that's kind of the idea of ownership, right? Which makes sense when you think about giving away physical objects. But of course, like, we don't always just give away everything we need. Sometimes you just want to transfer ownership. So a function can ask to borrow something. So this means that the function is going to expect to take a reference to an object of a given type. That's how values work in JavaScript land, right? You pass an object to a function, and they can modify it, and you can still modify it. That's unsafe, and so in Rust, that doesn't really work like that. But you can still say, hey, I want a reference to this object, and I'm just going to borrow ownership for that thing. And so it's similar to how it works in JavaScript, but with this slight extra level of checking around it. So what does that look like? So yeah, we have here the code where we're producing the simulation again, and we can use this little ampersand to take a reference to the simulation, and then we can pass that reference. So in this case, we're saying, hey, I'm going to, produce this reference and then blend it to this other function. But you can also take a bunch of immutable references, right? So in this case, they're immutable at the start. So by default, a reference will be immutable, but in our case, the initial barrier function is expecting a mutable reference. And so if we try to take two mutable references of something and then pass them to the barrier function again, we're going to break another rule. Again, the compiler is pretty helpful. We get these big helpful error messages, and it says exactly what the issue is. The fix for this one is slightly frustrating because you just have to reorder some stuff. So we can take the first mutable reference and then use it, and then take the second mutable reference and then use it again. And just like that, we have a happy compiler, which is a bit weird to fix a compiler error by just moving some lines around, but it's important to remember that like these are just things that you start to learn as you absorb and do more Rust, and we can all remember the weird things that we know about JavaScript by default anyway. So, while the borrow checker is pretty different from anything we've seen in TypeScript, again, just because we don't really care about memory that much, the concept of a type checker is hopefully quite familiar. But that said, there are a few differences. So, TypeScript by default has a structural type system. And so what that means is that if two objects are the same shape, they can be applied to the same type regardless of what the types are named. This is kind of based on the inherent like duck typing that we talk about in JavaScript land. Whereas if something behaves in a certain way, we want to treat it like the same type. But Rust, on the other hand, uses a nominal type system. And so if two types are identical, but they have different names and they're defined differently, they're treated as two totally different types. So they can't be assigned to each other. That might be familiar to you if you've done any Java or any other languages like that. TypeScript is kind of unusual in the way that it has a structural type system. I'm now running low on battery as well. Awesome. This is going to be fun. Okay, so TypeScript has relatively simple number types. So just this original number, and then more recently we've got the big-N type. Whereas Rust allows you to specify different size integers that are signed or unsigned, or floating point numbers. Yeah, so numbers are a bit different. Booleans, thankfully, Booleans are pretty much the same in all languages. There's, I guess, maybe some quantum stuff gets different there, but in current languages, Booleans are just true or false. String types, thank you. String types get a little bit more complicated too. So in TypeScript land, we just have strings, but in Rust, we have a few different ones. So we have the capital letter str string, string string. We have the shorthand str string, and we have a character type. So we can talk about individual characters as well. We'll talk a little bit more about how they're different too. The differences between these are kind of subtle, but they basically come down to mutability and then how much memory a string can use and how you can modify it. You can almost think of a character type as like a single character string literal type in TypeScript, if that's kind of helpful. TypeScript has a generic array type, and the equivalent to that in Rust is something like a vec or a vector. And then we have, obviously, the more complex types that we talked about a little bit before. So we have objects and classes, types and interfaces in TypeScript. And then in the Rust side, we have structs and implementations. Okay.
Okay, so let's write the renderer in Rust.
That's a great idea again. Let's give it a little go. So let's start by looking at the TypeScript implementation. So the canvas renderer has a single function called paint, which takes a simulation as an argument. It loops over each position in the simulation grid and checks if a position is a barrier cell. If it's something that the liquid's going to collide against, that gets painted black. Otherwise, it's going to pick a color value based on the velocity of that position of the grid. And then for some performance reasons, we update the image in a certain way before drawing it to the canvas. So in Rust, we don't have this HTML canvas API. So instead, for our default version, we're just going to render it to the terminal. So here we have a terminal renderer, which again has a single function called paint. It starts by rendering some kind of terminal control characters to clear out the terminal, resets to position 0. And instead of storing the result as an image, like we did for the canvas, we're just going to return a string, because we're just going to be printing to a terminal. So we're going to loop again. So remember, the simulation produces a 2D array, so we're looping through each line of the array one by one. Again, we do the barrier thing, so if it's something that the liquid's going to collide with, then we do a black. Otherwise, we look up the color in some tables and produce a nice color to get that nice pattern on the screen. After each line, we need to do some more terminal stuff. So we print that new line character out, and then we draw the whole thing to the terminal. And let's see if this thing is going to render. Okay, I think this one might work. Cool. So this is our little... It's not animating, is it? Yeah, it is. Okay, cool. So that's the terminal implementation of that canvas renderer from before. This is just a whole bunch of square blocks printing out one by one. But as you can see down the bottom, it's really freaking fast. Rust is really, really quick at doing the simulation step. Terminal's pretty slow. So now we kind of have that opposite problem, right? Before we had a fast rendering in the browser and a slow simulation, and now we have a fast simulation but a slow, low quality render. Cool. But in terms of the simulation, we can say that it is definitely faster. If we do an optimized run using cargo run with some release profile, kind of like a production build, we get that implementation, which is around 13 milliseconds for the simulation. And our goal from before was 16 milliseconds. So we're getting close. It's obviously a bit more granular than the canvas, so there's a few things that aren't quite the same, but yeah, we're definitely getting closer to being properly fast.
Ka-chow, did someone say faster?
We sure did. Okay.
You three, she's flaming hot now.
She's flaming hot now. Who wrote this?
How can we get that running that fast in my browser?
What an
Ka-chow.
excellent question. How can we get that running that fast in the browser? Well, Mr. McQueen, the Rust ecosystem has one more magic trick in store for us to try out. So WebAssembly has been floating around as an idea for a few years now, but the Rust ecosystem provides one of the most complete and accessible ways of creating WASM bundles to run in the browser. We only need to make a few little changes to our code, and we can prepare it to be compiled into WASM. First, we just need to import this WASM bindgen module, and then we use some little annotations to expose the relevant parts of our Rust code. So this is a kind of strange syntax. You can almost think of it like a decorator in TypeScript. And I know I said that pretty much all the tooling in Rust uses cargo. We're going to do something slightly different, which is use a tool called WASMPack, kind of like a Webpack thing for WASM. And this is going to produce a WASM bundle of our Rust code. So we've got this WASM version of our Rust, and now we need to interface with it from TypeScript, and that is a little bit weird. So first off, it kind of works. We can just import some compiled WASM code, but obviously the exported WASM kind of Rust hybrid uses these Rust conventions, so we unfortunately need to use them in our code as well. So instead of calling like new simulation, like you might expect, we're going to call simulation.new. And we also have to use bigints, which are also pretty weird in JavaScript land. We don't use these very often. That's because, like I said before, Rust is expecting unsigned 64-bit integers, and bigint is the closest proxy that we have for that. The one risk that you kind of have with a lot of this stuff is obviously we have JavaScript land and then we have WASM land. And the way to make this automatically slow is to spend a bunch of time passing things back and forward between these two bits of land. And so the way that we're going to do that is we're going to use this is called the float 64 array. These are memory managed buffers of memory that you can use in JavaScript. And we can provide the WASM part of this access to that memory. And so to do this, we kind of grab a reference to a position in WASM memory that contains the data, and we use a typed array to create a view over that memory. It's kind of just like looking at that memory. And this is going to be the way that we're going to read the data out of the simulation. Cool, here is my broken demo because my laptop isn't going to work. And now, just to make this real spicy, let's see if I can swap laptops on the fly and make it work. I'm like cautiously optimistic. Okay. Okay, cool. Let's see. Yeah, sorry, yeah, I'll go back after. Cool. All right. So that is our WASMified Rust version of the simulation running in the browser with the nice, shiny, beautiful canvas renderer. Not janky, looks okay, kind of thing. Yeah. Cool. Now we swap back so I can prove that this does work. Sorry, people. Thank you. Oh. Yes. Okay, so gives us what you just saw. And again, by the magic of measuring things, we can again lock the time that the simulation took and see that we're absolutely under our 16 millisecond frame per render, which means that our implementation is certified faster.
Ka-chow. I can custom tune my drag reduction system as I go.
Wow, we've achieved our goal. Isn't that a wonderful win?
That sounds like success to me.
Me too. Let's go over that one last time. So, Lightning McQueen always wants to go faster, and the dream is for him to use aerodynamic simulations on the fly as he's racing. But he can only use a web browser during the race, and TypeScript is too slow for this much processing. But Rust is really fast and can run our simulation really quick. And if we combine it with WASM, we can get it running super speedy in the browser and make Lightning a very happy car. And again, broken demo. Code is there. If anyone gets this to run on their own machine, I'll be very impressed because there's some bullshit going on. But pull that down, run the README, and it does look quite nice when you get it working. Yeah, I don't know. Hit me up on the internet if you want help. Ka-chow. The end. Once again, I'm Craig. Thank you so much for having me. All the organizers, thank you for help with that. Come find me, say hi. I'll be around. Yeah. Thanks.
You did it in the end.
Thank you.
Okay, folks.
Scared to touch anything. Hey.
Quick question,
Yeah.
maybe also a naive one. So for JavaScript, we have source maps to check on the dev tools in the browser.
Yeah.
Is there any tool that provides us with some kind of debugging feature, or like going to the original source map of the compiled Rust from the browser?
Great question. I'll be honest with you, the debugging experience for this is absolute trash. Especially when you consider what's going on. So we're talking from JavaScript into WASM. WASM already doesn't have great tooling. And then you're talking from WASM, which is the compiled binary into the Rust code. So I never got any kind of source mapping working. Cool community contribution idea, maybe. But yeah, no, it's this is for very, very specific use cases. It's cool that you can do this stuff. Actually making it work and actually making it like a usable dev environment, that's the real challenge here.
Thanks.
Other questions? One from home. Okay, Cosimo Lorusso. What about the Rust community and market demand? Does it take a long time to switch to Rust and use it?
Yeah, great question. I guess like it's a pretty fundamental question, right? Like, are there jobs in this stuff? Apparently there are. I'm a professional JavaScript developer. I don't ever have to write much Rust in my day-to-day life. The community is opinionated but helpful. There's a lot of resources around for how to build these things, how to start using it. It's not the most straightforward language. The borrow checker is a confusing concept. It's very different to writing JavaScript or TypeScript, even though the syntax is equivalent. I just wanted to try it out, so I tried it out, and I would encourage you to do the same. You might love it, you might absolutely hate it. I'm somewhere in the middle.
Thanks. And Andrea Bastianutti, is Rust suitable for embedded systems? If yes, how does it perform?
As far as I understand, yes. Again, I'm not a Rust expert by any stretch, but there is a big community of people who are building embedded systems with Rust, and I believe it is very, very fast. I don't know what it's comparable to, but people are certainly having success doing embedded stuff in Rust, so yeah.
Okay, Thank you so much, Craig.
Yes.